Hello everyone, welcome back to Diksha Karnataka YouTube channel. In the Decode NCERT series, today we are going to discuss a slightly medium important chapter, atoms. Right now your midterm exams is going on. Also, I need to complete at least two classes to complete ray optics. So we will start from ray optics next week. This week we will discuss slightly less important, medium important atoms, and on Friday we are going to discuss nuclei. Next week I will hopefully get some time to complete both ray optics part 1, part 2, because that is a long chapter. We have reflection, we have refraction, we have optical instruments. So that chapter I will take some time. So that's why I decided to complete this chapter as quickly as possible. So without any delay, let's try to reduce the discussion as short as possible, because our last class went little longer. So I know you guys don't have too much time to check, to read everything. So I will try to keep this discussion as short as possible. So let's see. So first of all, in the first paragraph, that is in the introduction, and if you are joining this series late, you should know that our one and only rule is that you have to open your NCERT book along with while I am doing it. That will help you to understand from where we are discussing, what we are discussing. Also, in case there are some problem while seeing this, you can check that from your textbook, right? So in the first part, in the introduction part, J.J. Thomson in 1856 to 1940, in almost about 1897, he discovered electrons. Okay, he discovered negatively charged particles and discovered electrons. Okay, based on that discovery, he first gave the nuclear model. So we know that in the past, since very long time, we know that atoms are indestructible particles. It was given by Kanad, it was given by Dalton. So there are a lot of versions of that. Based on that, it was assumed that everything that we see are basically solid. Okay, nothing is there. Okay, everything is solid and everything is constituent and everything is only one piece, right? But when J.J. Thomson discovered electrons, so he thought, okay, maybe everything is solid. So how it is like solid? He thought of the model. First he he thought of an atomic model where he thought it is like a cake or a plum cake. You may have seen plum cake during Christmas. So plum cake, where electrons, which is individual particles, are embedded inside that. So like cashews and raisins and fruits, that is embedded inside a plum cake. So everything is embedded inside that positively charged base. Okay, that model was known as plum pudding model, but it was a huge failure. We will see that why. So we know that condensed matter, solids and liquids and dense gases at all temperatures emit electromagnetic radiation, in which the continuous distribution of several wavelengths is present. Though with the different intensities, this radiation is considered due to the oscillations of atoms and molecules governed by the interaction of the atom or molecules with its neighbors. In contrast, the light emitted from a rarefied gases heated in the flame or excited electrically in a glow tube, such that the familiar neon sign or mercury vapor, light has only certain distinct wavelengths. So for example, when you heat up some object, generally we are expected to get all the lights, but when you reduce the intensity, reduce the amount of light present in that tube, and if you electrically heat it, you get different colors, like neon signs. You may have seen neon signs in different stores. Okay, red light, blue light, yellow light. Okay, they are called neon signs. Once upon a time they were very popular. Now we do not use neon sign. We mostly use LEDs. Colored LEDs are sufficient, and since we have invented colored LEDs, nowadays we only use colored LEDs. But neon signs was very popular, maybe around 1970s, 1980s. Okay, most of the posh restaurants and posh areas, they used to mark their names using neon signs, so that people are thinking, okay, they are this is a very high end restaurant. Okay, so that is one thing. But you should remember that the old tube light, you may have seen that old structure tube light, where you used to get a white light. Okay, based on the color, that gas that you are using inside, you might get different colors as well. You can get yellow, you can get red. So now those tube lights, how they are manufactured, what is the principle of that, they are not able to explain. Even though it is observable, we were not very clear about the whereabouts of the physical interpretation of that phenomena. Okay, so first person who started doing some experiment was Henrik Rutherford. Okay, Ernest Rutherford in 1911 he suggested some experiment to Geiger and Marsden. Okay, perform some experiment. So the idea was of Rutherford, and Geiger and Marsden performed the experiment. That's why it is called Geiger-Marsden-Rutherford experiment. Okay, even though in popular theory it is only talked about Rutherford experiment, even though actually it is not done by Rutherford himself. Okay, now what is the Rutherford experiment? There are a lot of description. You can read the entire description, but main thing that you have to remember, that the alpha particle that is used in Rutherford experiment is of the order of 5.5 mega electron volt. Once upon a time I have seen an MCQ where they asked the energy of the alpha particle used in the Rutherford experiment is. So you have to remember it is of the order of 5.5 mega electron volt. There is no need to calculate. This is just a memory based question. And from this chapter a lot of small MCQ comes. So that's why this chapter is slightly important in terms of criticality of the questions. Okay, a lot of question comes, but you can answer them if you study the chapter properly. Right, now this is the schematic of the Rutherford experiment or Geiger-Marsden experiment. Now in this year preparatory pre-board exam in Bangalore South question paper, this was asked. Okay, draw the schematic of the Rutherford experiment as a 2-mark question, which I believe is not super important, but if you want, you can practice this diagram. There will be some questions obviously which is not super common, not highly expected, but there will be a question paper consists of not only 70 marks, it is more than 100 marks. So you have to only answer 70 marks out of the 100 marks. So there will be some questions, some extra questions which are not common. Right, so this is one of such question which was not common but asked sometimes. So you might practice if you want, but in my opinion, just to understand this how this is done. So we have a sample material of gold. So this is from the top view. This is the top view from where you are observing. Okay, the source of alpha particle. So this is the actual system. Okay, and from top, if you see, you will view like this. Okay, this is the schematic diagram. This is called schematic diagram. The gold leaf is placed like this. Here the source of bismuth. Okay, alpha particle is excited from the excited bismuth, radioactive bismuth, from where alpha particles are channeled through this. Okay, and here we have some detector which can rotate around a rail, and it can measure what is the percentage of particles coming at different angles. Okay, this is how they measure the scattering angle. This is how they measure the intensity as well. So more light is now let's move on. Okay, now what is the observation of this experiment? Observation of the experiment is written here. Many of the alpha particle pass through the foil. So what we are expecting? We were expecting that it is a solid. So what is the experiment? Briefly let me tell you. So there is a gold foil, some alpha particle is hitting, and it's like you are throwing balls towards a wall. Okay, there is a solid wall and you are throwing multiple balls. What you are expecting in that experiment? So in that experiment you are expecting that 99.9% balls will come back towards you directly, right? So if you throw balls, maybe 1 or 2 balls might break and they fall near the wall, but none of the balls are expected to go other side. right? And almost all the balls will come back towards you, maybe some 1 or 2 balls which will break and they might fall. That is also part of the experiment, so you can keep that in mind. So when you are hitting the ball towards the wall, you are expected to get back all the balls towards you, right? Similarly, in this experiment was also like that. We are expecting, when we are performing the experiment, if the palm pudding model was correct, then most of the balls supposed to come back towards us. But what is happening here is like most of the alpha particles, almost 99.9% alpha particles are actually passing through it. So you are throwing balls towards the wall, but instead of hitting the wall, it is going through the wall. So that is what if you see some kind of experiment like that, then that will be something which is amazing, right? So you have to be thinking what is happening here. So many of the alpha particle pass through the foil. It means that they do not suffer any collision. Only about 0.14% of the incident alpha particles scattered by more than 1 degree. So 0.14, so 99.86% pass through directly. Only 0.14% scatter more than 1 degree. Okay, and about 1 in 8,000 deflect by more than 90 degrees. So 1 in 8,000 they scatter, they somehow come back towards you, otherwise all the particles, all the balls that pass through the wall. Okay, so Rutherford argued that to deflect the alpha particle backwards, it must experience a large repulsive force. Okay, so basically what is the conclusion? That whatever model, palm pudding model they suggested is completely wrong. So most of the space inside of an atom is empty. Okay, it provided and when some part is coming back, that means they are experiencing some kind of repulsive force. Why repulsive force? Because alpha particle are positively charged. So positive charge is getting repelled by another positive charge. That's why it is coming back towards us. That means it is getting repelled by a high order positive force. Okay, it is provided a part of the mass of the atom, and it is positive charge were concentrated tightly at its center. So what he said, most of the part of the atom is empty, and in most of the mass of the atom is tightly packed inside a center small area, and that small area is definitely positively charged. Okay. So then the incoming alpha particle could get very close to the positive charge without penetrating it, and such a close encounter would result in a large deflection. This agreement supported by the hypothesis of the nuclear atom. This is why Rutherford is credited with the discovery of nucleus. Very important. So discovery of nucleus was credited to Rutherford. Okay, so this is very important. You have to remember that who discovered nucleus? Nucleus was discovered by Rutherford. Okay. Now this is a graph. Okay, this is a graph. As you can see that nowadays there are a lot of graph related questions in your KCET or maybe in your PU objective exam. So they might give you 4 graphs. So you have to identify that when the angle of degree is less, okay, for higher number of particles. So most of the particles are getting without any deviation. Okay, and as you are increasing the angle, okay, 90 degree deviation, this is 90 degree deviation, this is 100 degree, 20 degree. So as you are increasing the deviation, so number of particles is very less. Okay, number of particles is almost getting 0, and they have tested with a very large number of particles. Okay. Rutherford experiment suggested that the size of the nucleus, now that small area where everything is concentrated, that part is called the nucleus, right? Nucleus means the center of everything. So according to Rutherford, the nucleus, size of the nucleus is about 10 to the power of minus 15 meter. Okay, so very small. To 10 to the power of minus 14 meters. So size of the nucleus is about 10 to the power minus 15 to 10 to the power of minus 14. From kinetic theory, the size of an atom was known to be 10 to the power of minus 10 meter. You have studied this in your PU1. You can go back and check chapter 10 section 10.6 in class 11. Okay, so in your first PU you have studied it. In your physics textbook you can check. So from the kinetic theory, the size of the atom is already known, that is about 10 to the power of minus 10 meter. Okay, so atom is almost 10,000 to 100,000 times bigger than the nucleus. So atom is very big, but nucleus is very small. Okay. Thus, the most of the atom is empty space. Most part of the atom is empty space. However, when alpha particle happens to come near to the nucleus, the intense electric field there scatters through the large angle. The atomic electrons, being so light, do not appreciably affect the alpha particles. So alpha particles are only affected by the nucleus. They do not get affected too much by the electrons, okay, because they are very, very light, and charge is okay. Charge part is alpha particle has more charge than electron. Electron has only one charge, alpha particle plus 2 charge. So they generally don't get deflected too much by electron. That is negligible, okay. The magnitude of the force that is between the nucleus and the alpha particle is given by this. You can start from this equation and remember it, or you can just remember this equation, okay. This is easier to remember this equation, okay. 1 by 4 pi epsilon. So basically two charges. So Z is the atomic number of the nucleus. We will learn about it in our next chapter. 2 is the charge of the alpha particle, and Z is the charge of the nucleus. So the distance is, this distance is, we will define it in a next part. So the trajectory traced by an alpha particle depends on the impact parameter B of the collision. The impact parameter is the perpendicular distance of the initial velocity vector to the alpha particle from the center of the nucleus. So this distance, remember that. So this distance is called the impact parameter. Further away it is from the center, central line, okay, impact parameter will be very, very high. Okay, further it is away from the central line. This is the central line that is towards, exactly towards the nucleus. Okay, if it is exactly going directly towards the nucleus, the impact parameter is 0. Okay, for a direct collision, impact parameter is 0. You have to remember that. It is seen that an alpha particle close to the nucleus, small impact parameter, suffers the large scattering. So smaller the impact parameter, larger is the scattering. In case of head-on collision, the impact parameter is minimum and alpha particle rebounds back. So if it is directly going, so alpha, in that case impact parameter is 0. If impact parameter is 0, in that case the deflection is pi degree, pi, okay. For large impact parameter, the alpha particle goes nearly undeviated and small deflection. So from this paragraph, a lot of questions, MCQ questions are possible, okay. For what is the impact parameter for head-on collision? What is the impact parameter if the deflection is 180 degrees? What is the impact parameter if the angle of deflection is 0 degrees? So you have to be careful and answer such questions, okay. We'll see that again in our MCQ Chakravyuh series when we come to this chapter, but this part you have to remember for MCQ part, okay. The mass and positive charge of the atom is concentrated at the small volume. Rutherford scattering therefore is a powerful way to determine the upper limit of the size of the nucleus. So from Rutherford scattering experiment, you can determine what is the average size of the nucleus, what is the maximum possible size of the nucleus. Now electron orbits. So now Rutherford says that obviously the electrons are orbiting around the nucleus. Nucleus is positively charged, located at the center, and all the electrons that was discovered by Thomson, that those electrons are rotating around the nucleus. At this point of time, nothing else is known. Only thing was known as positive charge of nucleus. We calling it nucleus, that is located at the center, and everything is rotating around. All the electrons are rotating around the nucleus. Okay. Now it is very, very familiar model, our solar system model, right? In solar system also planets are rotating around the central mass, that is sun. Similar to that, he also said the same thing, and you can calculate the velocity of the electron using simple mv square by r, that is the centripetal force. Okay, and the radius also can be calculated. Radius can be calculated in this formula. Energy can be calculated using this formula. Even though that is not super important, if you are preparing for any competitive exam for JEE, you need to remember these formulas. Okay. The total energy of the electron is negative. This implies that, so here you see that formula, total energy is negative. So what is the meaning of that? This implies the fact that the electron is bound to the nucleus. If E were positive, an electron will not follow a closed orbit around the nucleus. So energy is positive, it will be free. Okay, if energy is negative, that means they are bound to the nucleus. Now atomic spectra, this is another important concept. When an atomic gas or vapor is excited at a low pressure, okay, the emitted radiation has a spectrum which contains certain specific wavelength. So if you heat up a gas or some material, okay, at low pressure and high temperature, okay, there are different ways to do it. Electricity is one of them. You will get some specific lines. Okay, specific line means, for example, yellow line, blue line, they are all represent some line. Okay, red line, ultraviolet line, it can be, we will again know about it in electromagnetic waves chapter, what is the meaning of the line. But line means a color basically. Okay, you will get some color. It can be visible, it can be invisible, okay, but you get some specific line. Okay, for example, if I heat sodium vapor, okay, I will get sodium D1 and sodium D2 lines, two yellow lines. Okay, the yellow color slightly different, so you will get two colored lines, yellow lines, they are called sodium D lines. So based on what, if you are heating helium, you will get certain colors. Okay, you will not get single color, there are some more number of colors. Okay, so based on what lamp you are using, what gas you are using, basically that's how the helium lamp, the halogen lamp, you may have heard about halogen lamp. So that's how the terms came in, though even though the halogen lamp and the halogen lamp that we use are slightly different, but that's how the name came into effect, that we are heating a gas, okay, and they are emitting some light. Okay, and these lines are called emission line spectrum. Very, very important. So for example, here they have shown the emission line spectrum of hydrogen. So you can see that there are certain lines. Okay, some of them are in visible region, specifically some wavelength of Balmer series are in the visible region. That means if we get these lines, we can see this using our naked eye. So these colors you will be visible in the naked eye. So if you are using hydrogen lamp and you are doing some experiment, you will see these colored lines. Okay, instead of these black lines, you will see the colors. Okay, and some lines will be on the infrared side, some light will be in the ultraviolet region, that will not be visible in naked eye. You have to use some sensitive material to detect those lines. Okay, study of emission line spectra of a material can therefore serve as the type of fingerprint for identification of the gas. So they are unique for individual gases, individual materials. All materials have different characteristic spectrum. Okay, this is called characteristic spectrum. That means it is characteristic of sodium. This is characteristic. Here it is shown the characteristic of hydrogen. So if you see this kind of graph, this kind of spectrum, then you can definitely say this is a hydrogen spectrum. Okay, so that's why this is called fingerprint. Fingerprint of different person is different. Similarly, characteristic spectrum of different materials are also different. Okay, when white light passes through a gas and we analyze the transmitted light using a spectrometer, we find that some dark lines in the spectrum. Now what we are doing now, now gas is not excited, gas is in normal temperature. Now we are allowing white light to pass through it and you are observing the lines. In that case, the white line should contain all the lines, right? It is almost perfect light for visible region, of course, but instead of that you will get some dark lines in that spectrum as well. Okay, so that correspond to the precisely the wavelength which were found in the emission spectrum of the gas. So emission spectrum, when you are exciting the gas, they are emitting those lights, but if the gas is not excited, you are just allowing normal light to pass through it, they are absorbing those lights that they are supposed to release when they are excited. So normal condition, they are absorbing that light. In excited condition, they are exiting the same light. Okay, so that is why they are called dark spectrum. Okay, they are absorbed, so that's why they are dark, and this is called absorption spectrum. So emission spectrum, absorption spectrum, both are complementary. So if you mix emission and absorption spectrum, you will get a complete wide band. Okay, now Bohr model of hydrogen. Before knowing into Bohr model, let's see what are the drawbacks of Rutherford atomic model. They are not directly given, so you have to, I have highlighted them for you. First drawback is an accelerated charged particle emits radiation in the form of electromagnetic waves. So the energy of an accelerating electron should therefore continuously decrease. The electrons would spiral inward and eventually fall into the nucleus. So this is the another line. the electrons would spiral inward and eventually fall into the nucleus. Okay, so this is the nucleus is very short lived. So as soon as it is forming, it is getting destroyed, which is not at all we are seeing, right? We are, if the nucleus was destroyed, if the atom was destroyed, then you, me, this world would not have been possible. But we are here. That means the atom is not self-destructive, right? They are sustainable. So as the electrons spiral inward, their angular velocities and hence their frequencies would change continuously, and so will the frequency of the light emitted. Thus they would emit a continuous spectrum in contradiction to the line spectrum we actually observe. So now also, if this is happening, if the electrons are orbiting and continuously falling towards the nucleus like this, okay, then what would happen? They would emit all possible radiations and we will get a continuous spectrum instead of this line spectrum that we see for hydrogen. Also I gave you one example for sodium. So those are not possible. Every light would have been there. Okay, only specific frequencies, specific lines were not possible. Right, so that is why these two are the main drawbacks of Rutherford's atomic model. So his student Bohr came up with another atomic model similar to that of Rutherford, but he said my atomic model is very strict. They has to follow some rules. What are the rules? So that rules are called postulates. Postulate means they are true to all the words. Okay, they might not agree with the current physics, but it has to be true, then only it is possible. So what are the postulates? So Bohr's first postulate was that an electron in an atom could revolve only in certain stable orbits without the emission of radiant energy. So he said that electrons will rotate in the around the nucleus, but the orbit will be very fixed. So the angular velocity, the Bohr's second postulate defines this thus: this stable orbit postulate the electrons revolve around the nucleus only in those orbits for which the angular momentum is the integral multiple of the h by 2 pi, where h is the Planck's constant, that is 6.6 into 10 to the power minus 34 joule second. Thus the angular momentum L of the orbiting electron is quantized, that is it is an integral multiple. L is equal to nh by 2 pi, n is 1, 2, 3, 4 or 5 like that. Okay, so Bohr's third postulate incorporate into the atomic theory that early quantum concepts that had been developed by Planck, that is the energy emitted. So what is that? He said that when it does so, the photon is emitted having energy. So when electron jumps from higher energy to lower energy, it emits some photon. Okay, the difference between the initial and final states, the frequency of the emitted photon is given by h nu is equal to ei minus ef. I hope you are you are familiar with that. The radius of the Bohr's orbit is given by this formula, and energy of an electron in a Bohr's orbit is given by this formula. Okay, here n is a quantum number, principal quantum number, we call it n is equal to 1, 2, 3, 4, 5, 6 positive and integer. Okay, 1, 2, 3, 4. It starts from 1 and it goes to infinity, but in an integer way. Now, energy levels, the energy of atom is the least, that is largest negative value. So least means largest negative value, minus 13.6, minus 13.6. Remember that when it is electron is revolving in an orbit closest to the nucleus, that is 1 for which n is equal to 1. For n equals to 2, 3, the absolute value of the energy E is smaller, hence energy is progressively larger in the outer orbits. The lowest state of the atom, called the ground state, is that where the lowest energy, so lowest energy where the energy is least, highest negative, that is called the ground state. For example, n is equal to 1 is ground state for all atoms. Okay, it is the lowest energy with the electrons revolving in the orbit of smallest radius, the Bohr radius a0. The energy of this state is minus 13.6 eV. So 13.6 divided by n square, so n is equal to 1 means minus 13.6 eV. Therefore, the minimum energy required to free the electron from the ground state to the hydrogen atom is 13.6 electron volt. This is also a MCQ question. What is the minimum amount of energy required to free up an electron? It is called the ionization energy of the hydrogen atom. Now if you see the graph of that, see this is the ground state, this is n is equal to 2, the gap is quite significant, but as you are going up and up, all the energy levels are combining with each other, they are falling onto each other, so they are basically merging with each other, right? Now there is one example is given, the energy required to excite one electron from ground state to E is equal to 2 is 10.2 electron volt. You can check it out in KCET, the exams, in KCET exam. These kind of problems are very common. Now H nu is equal to ENI minus ENF, the same formula we have seen. In 1922, Bohr was awarded Nobel Prize in Physics because of his contribution. So obviously Bohr was awarded a Nobel Prize. So that is what I think is important. Now as de Broglie's explanation of Bohr's second postulate, which is very important, based on that question comes. You can check my Brahmastra series, I have discussed briefly about that, but main thing is 2 pi Rn is equal to n lambda, that is what said he said. So if quantum number is n, they will make closed gap, okay, it will be like a static wave, so the electrons moving in a form of wave and they will form static wave, and that wavelength can be calculated using this formula. So this formula is also important. Based on that, a lot of questions might come, and from there they have compared it with this formula and they have calculated the angular momentum. Angular momentum comes out to be nh by 2 pi. But this is important, an electron is orbiting in somewhere, what is the wavelength? You can calculate it using this formula. Okay, this model is, however, has many flaws. So even though Bohr's model apparently reduced most of the problems, it still has some flaws. Let's check one by one. The Bohr model is applicable to hydrogenic atom. It cannot be extended to two electron system such as helium. Okay, while Bohr model is correctly predicts the frequencies of the light emitted by the hydrogenic atom, the model is unable to explain the relative intensity of the frequencies. Bohr model presents an elegant picture of the atom and cannot be generalized to complex atoms. Okay, for complex atoms we need quantum mechanics. Now this is the summary, you can read the summary once, and points to ponder also you can read it once. With this we have completed this chapter. We will be back with a nuclei chapter on Friday. Till then, bye.